record your screen and I'll put the chat down. Okay. So everything is there. Does anybody want to talk about anything? We still got stuff to talk about, and as far as chemistry, is there everybody doing well? Did you have a nice week off? I mean, I was chatting to, how about you, Dennis? Did you have a good spring break? Yeah. Oh, cool. Oh, fun. You said it was at Lanai, you said? Yeah, cool. Yeah, I mean, because they don't have Costco there and stuff. There's only I remember there's the Blue Ginger Cafe, right? And then there's like one grocery store. Yeah. Also, you ferried over. Oh, cool. Yeah.
So the last lecture you mentioned about only sulfuric acid is we have to do two separate ice.
Yeah.
How do you get for the change 0.001?
Okay, so we're going to go back. The question was why do you, so for sulfuric acid, it was a specific question for sulfuric acid. So that was, is it this one? Okay. So way back here for sulfuric acid, you're wondering, is it this change right there?
No, the other one. So how do you get 0 on the left side, 0.01?
Which, that one here?
Yeah, like, and the other ones too.
Okay, so here is, so the pH of centimolar, 0.01 molar sulfuric acid.
Okay.
So I mean, you have two ice charts. And step one, this step, it's just an arrow. Okay. So meaning like it only goes, I'm saying this reaction goes completely to the right. It's a strong acid, so that means it completely disassociates. So, which actually is mostly true. It doesn't always disassociate. One of the major catalysts for it is sunlight or just any light. So, I mean, unless you're carrying this reaction in the complete dark, there's no visible light, then if there's any visible light, it's going to break apart. So that's another interesting, that's just a random factoid. But anyways, sulfuric acid, the first hydrogen is strong, which means it completely shifts to the right. And the idea is that we don't have to do an equilibrium, that we shift completely to the right, and then all of the sulfuric acid, so all of the H2SO4 is consumed completely, and that means that 0.01 of this is then going to generate 0.01 of each of the products, and you have nothing left over. Does that make sense? Yeah. And then now you have step two, where you have the equilibrium, and then you have to do the Ka and do all the variables. Does that make more sense?
Yeah.
Oh. Yeah, that's a hard problem, and it was one of those, like, believe it or not, I mean, like with the pandemic, I've gotten a little bit of social anxiety, but the nice thing is I'm getting over it. And I was a little anxious. I'm like, oh gosh, I hope I don't screw that one up, because it's a hard problem. It's not that I'm not smart enough. It's just they're so easy to screw up because there's so many little steps. So, but that's always a tough one. Other questions? Okay, good question. All right, so now we're moving on to chapter 16. And so I was even reflecting about this over spring break. I'm like, wow, we're like over the hump for the semester. And in a way, thinking about this class, it's probably going to start getting easier for you. So like one of the things about this class, it kind of smacks you, like it's it's kind of an easy, you kind of ease into it like in the first 2 weeks, and then you just start getting smacked with these really hard concepts, right? And then you get hit with kinetics, which is the hardest chapter in the book, and then you get to equilibrium. You're like, what the heck is this stuff? And now actually we're kind of over the hump, and we're going to start getting a little easier. It's same types of problems, but like it's a lot easier. Like it's like you start seeing the finer points, and once you get over like using the logarithms, and it's easy. So actually, hopefully you'll find this class getting easier as we move out. And I even was thinking about my life, and I was like, wow, it's like almost in the springtime now. It's funny how time flows, and it's kind of scary how quickly time can flow. Anyways, so we're going to go into aqueous equilibria, but in other things. We were talking a little about acids and bases still, but we're going to talk specifically about something called buffers. So, but before that, talk about ethylene glycol poisoning. And so I remember seeing this, like I went to Glacier National Park in 2019 when we were free to move around. And like there were these goats, these mountain goats, they kept on licking the pavement because sometimes cars release, ethylene glycol, antifreeze. And they love licking. There's one male goat that was just spent all his time licking the pavement because he was looking for ethylene glycol. And I mean, there's not enough of that. It was a pretty big goat. I mean, it was like 600 pounds or something like that. It was huge. So, but it probably wouldn't be enough to harm it. But I mean, if you have like a cat or a dog starting to eat ethylene glycol, it can, and also humans, I mean, it can kill us and the smaller animals a lot more quickly. Although humans are pretty good they're good patients. Animals are not very good patients. But so ethylene glycol poisoning. So your body, one of the major ways when you incorporate something to the human body, your body very frequently tries to oxidize it. Like what the heck is this stuff? I don't know. I know. Let's oxidize it. So your body does that for everything. Alcohol, most toxins. If you inhale benzene, your body's going to oxidize it. So, but ethylene glycol, it oxidizes and it forms glycolic acid. And glycolic acid is an acid, and that lowers the pH, right? So acids lower pH. And the problem with this is it creates a condition in your blood called acidosis. And an issue with acidosis, there's a couple of things. Your oxygen carrying capacity goes down, and you can also denature proteins. You're under depends on how bad the acidosis is. Your organs can start to fail. So that's one thing with patients, like human patients or any patient. We're very picky. Like our blood saturation, oxygen saturation needs to be pretty high. It needs to be in the 90s, right? If it drops below the 90s, that's bad news bears, right? The patient, it hurts. Like I don't know if you've had a low oxygen concentration. I get that with altitude. It's not comfortable. And acidosis, I had acidosis once. It was from Volcano into Volcano National Park, and it started to erupt, and I breathed in too much sulfur, and man, I felt like crap. It wasn't that bad. I didn't have to go to the hospital, but one of the ways you can get around it is, well, one of the things that I started happening to me is I was hyperventilating. And the reason why you hyperventilate, among other things, is so we have carbonic acid. That's how, or carbon dioxide dissolves before carbonic acid, and that's an acid, right? So that raises your blood pH. But then when you exhale, you breathe out carbon dioxide. And if you start hyperventilating, you can create a condition called alkalosis, which means your blood's pH is too high. So acidosis is too low, alkalosis is too high. It's harder to get alkalosis. It's much easier to get acidosis. So other things maybe you've heard of, so ketosis or ketoacidosis. That's if you are on a ketogenic diet, or if you're starving, So if you have very little carbs or you don't eat at all, your body starts to break down its own tissues, and it creates a condition called ketosis, or also I guess officially ketoacidosis. And I've had that before too. That's your breath gets really sweet. It's one of the things, people that have very sweet smelling breath, because they're breathing out ketones, and ketones are very sweet smelling. But so anyways, so our blood pH is very important. It really needs to stay around 7.2 to 7.4. And if it's not in that range, then bad things starting to happen. What can happen is your proteins can change shape. If they change shape, they don't work as well, and then organ systems can fail, and tissues can be damaged. And if too many of those fail, then the patient dies. So also, besides that, is oxygen carrying capacity. I mean, which is also important, obviously, but usually patients die from organ systems failing. So the blood needs to regulate pH very well. But well, actually, does anybody want to guess? Besides, well, one of the ways you can treat acidosis is you can inject patients with sodium bicarbonate, so baking soda. But do you know another way to get over ethylene glycol poisoning? Get really, really drunk. There's two things that'll do that: methanol poisoning, ethylene glycol poisoning. Well, it only works at the start of it. So because like if you, it's like, I don't know if there was one of the, I think the first season of Simpsons, they were putting ethylene, someone in France was putting ethylene glycol in their wine. But I mean, like, if you drink alcohol with it, either your body preferentially goes after the ethyl alcohol. Same thing with methanol. So it's even written in the material safety data sheets that if, like for methanol, if any student or anyone ingests it, give the person some ethanol, and send the person to the hospital. But one of the treatments is they can inject you with a 10% alcohol solution. And man, talk about going from 0 to drunk real fast, right? So anyways, so that's one of the treatments, but it only works in the beginning, because methanol can oxidize to formic acid, and then besides, formic acid also is a neurotoxin, specifically to the optic nerve in your eye for some reason. But it's that ethylene glycol. If I had to pick one, I would pick ethylene glycol poisoning over methanol poisoning, although that's, which one, how would you like to be poisoned, kind of thing. But this one it doesn't react as severely, at least at first. And that's also easy to treat. So only do that if you're like alone on Lanai and you accidentally, drink a cup of ethylene glycol or antifreeze. Like, all right, break out the alcohol, send me on the ferry. But but it's probably, I mean, if something happens, it's always better to call poison control. Yeah, but I'm just kind of telling you, interesting little tidbit. So, okay, and because of that, I mean, obviously with blood having a very tight range in pH that it can work, our body needs to regulate pH very closely. And we have something in our blood called a buffer. And a buffer resists the change in pH. So what a buffer does is it resists pH change. Another story. I remember I was slicing limes one time, and lime juice has a pH of 2, and I cut my finger with the lime knife, and man, that hurt. Right? I mean, that was one of those that really, I remember distinctly how bad that cut hurt with. I mean, not that cuts, are ever pleasant, but I remember that one particularly stinging because, like I said, pH of 2, and blood has a pH of about 7, 7.3-ish. So I mean, that's a 10 to the 5. That's a 10,000 times difference. I mean, So a little bit of drop of lime juice went into my cut in my finger. You know, that's a factor of 10,000 times. Why didn't my finger just completely disintegrate from that? All the cells in there. It's because I have a buffer in my blood. So I mean, the buffer took care of that. So that way I wouldn't have died from a little bit of lime juice in my blood. So, and where the buffers come from, it has a weak acid and conjugate base, or it can have a weak base conjugate acid, but most of the buffers are usually on the acidic range, at least the ones we use. So weak acid, conjugate base. And so because of this, if you add acid, if you add base, the acid will neutralize the base. If you add acid, the conjugate base will neutralize it. So here's an example of one. So you have acetic acid and sodium acetate. So this is the acetate anion. So this right here, that's the conjugate base to this acid. And since you have both in the solution, adding a little bit of acid or base doesn't change the pH all that much. And then we come to this equation. This is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the base to the concentration of the acid. Or you can also think of it as the moles of base or the moles of acid, depending on what you do, because concentration is moles per liter. So you can get rid of the liters and just have the moles. So from this, and this equation's, I think it's the second most important thing you can learn in this class. I think the most important thing actually is the Chatelier's principle, the equilibrium shifts. So I mean, that's remember that equation, well, that concept. I think that's probably the most important thing to learn, at least singular concept, other than, you know, of course, general problem solving and math skills. But if I had to highlight the most important thing, I'd say the Chatelier's principle. If I had to highlight the second most important thing, it would be this one, because you're going to use this, especially in the bio people, I guess. So I forgot, Dennis, what are you? What's your major? Okay. So I guess you won't use it as much. Bio people use a lot more. I didn't use this as much with my research, but especially bio people use this a lot. What? Gotcha. You could write it that way as well. I mean, that'd be a different equation. Go ahead. Oh, yeah, we can, depends on the context of the problem, but yeah, we're about to do an example. Very good question. So, but as far as adding, then you'd have to look to see how, you'd have to do this first, the example like this first, and then see how it changes. So we can, I don't know, do I have a problem like that? I guess not. So I have one in the homework. So here's an example problem. Calculate the pH of a buffer of solution that is 0.05 molar in benzoic acid and 0.15 molar in sodium benzoate. So use this equation, and this is, can you imagine this for the ice chart? So this is what it would be for the ice chart. So you would write, so I'm just going to do acid. So it'd be benzoic acid in equilibrium with benzoate plus, I should say, it'd be H plus, so ICE. So initial, it would be 0.05, benzoate would be 0.150, so we shift right. Equilibrium 0.05 minus X, 0.15 plus X, and then the Ka equals 6.5 times 10 to the minus 5 equals x times 0.15 plus x all over 0.05 minus x, right? And then solve for x. That looks like a pain in the butt. Instead, we can just do the Henderson-Hasselbalch equation. So the pH equals the pKa, which is minus log of 6.5 times 10 to the minus 5, plus the log of the concentration of the base. So the base is 0.15 over 0.05. So you just do that in one fell swoop. And where is that? And doing that then, it's going to be 4.74. So you see here using the equilibrium method, it takes a lot of steps. You have to set up the ice chart, really think about things. This one is just, it's literally just a plug-in called a plug-in chug, right? You just use the equation, you plug in the values, and it spits out the answer. So hopefully for you guys, like, gosh, it's about time, right? So about time we had a nice softball thrown at me. So so for this equation, introduction to using the Henderson-Hasselbalch equation, actually this equation is derived from using the x is small approximation. So, but pH is equal to pKa, which is the minus log of the Ka, plus the log of the concentration of the base of the acid. So we just, if we know the Ka, minus log of that, and plus the log of the base is the one that says sodium in front of it. It'll say, which one is the base? It's the one that says sodium, potassium, whatever acid. And then the acid is usually the one that has acid in the name. So benzoic acid is the acid, and the sodium blah, blah, blah is the base. So then the log of the base of the acid is 0.15 molar over 0.05 molar. And then don't forget the pKa, and you get the answer. So I'm kind of going like what the major questions are from students in the past. Which one's the acid? Which one's the base? The acid is the one that says acid in front of it or after it. Typically, like acetic acid, citric acid, hydrochloric acid, sulfuric acid. That's the acid. And the base is the one that has an alkali and then the name. So sodium benzoate, lithium benzoate. We usually in biology, we usually use sodium or potassium. Is more commonly used. So questions with this one? All right, let's see if you can do this one. It's 0.25 molar hydrogen cyanide. This is the acid. And this one's the base. I know I didn't say hydrocyanic acid, but the acid has the extra base, or extra H has the extra base. Acid has the extra H. Let's see if we can figure this one out. Oh, this room smells like a dentist's office again. I must have cleaned it every spring break. Do you guys smell that, or is it just me? Does it smell like a dentist's office? Yeah. I remember that at the beginning of the semester. I was wearing a mask when I came in, so I didn't smell it, but it's that kind of cleaner. Well, at least you know it's nice and scrubbed down. I can't do this for all the problems because the calculator app I used to use doesn't work anymore. I know. This one is just a straight shot. Or did you, this, I guess I should have checked. So are you guys following? Do you have any questions? Usually, yeah, go ahead, thanks. Why is it so big? Yeah. Yeah. So why is the pKa so big? It just depends on the size of the Ka. So let me pull up some data. I'm gonna look in the back of the book. It has to do with the size of the equilibrium constant. The answer is the size of the equilibrium constant. Okay. So here are some acids, and here are the Ka values. So let me just do some of the. It just depends. Like I said, just depends on the size of the equilibrium. So log. We'll do formic. Wouldn't let me do that. All right. Log. Okay, so formic acid pKa. This is going to be 3.74, and this is at 9.31. And I'll do hydrofluoric acid. And I'm just doing, this is this minus log of 6.8 times 10 to the minus 4. Log. So this is going to be equal to 3.17, and I'll do a big one. I'll do hydrogen peroxide minus log 2.4 times 10 to the minus 12. Exponent 12. Okay, so this would be 11.62. All right, and the point I'm trying to say here is it just depends on the size of the Ka value. So someone like formic acid is going to have a pKa of 4-ish, and then hydrogen peroxide has a pH, around 11 to 12. So solutions, therefore, then when you have solutions of these things. The formic acid, the formic solutions are going to tend to be in the acidic range. And if you have a buffer that has something like cyanide, I even call it cyanide, hydrocyanic, but most everyone, I guess, commonly would call it cyanide, and peroxide. Those tend to be, then they tend to be more in the alkaline range if you have a buffer in those ranges. So that makes sense. But if you have just a solution of cyanide, like hydrocyanic acid, it's going to be in the acidic range, slightly in the acidic range, like pH of 6. So, but a buffer solution is going to be 9-ish. So, does that answer your question? Okay. All right. So, one of the things I want to talk about, though, is kind of the way that you approach a function. So this is more of a math concept, right? So you have y. Y is a function of x, right? So when you have an x, y, and you can get some random function. So when you look at a function, actually, maybe I'll change the axis color. So here is a blue function on an x on a black axis. So certain things you can tell just by looking at the function. So what can you tell from this? So there are 1, 2, 3, 4. There are at least 5 real roots this equation. So real meaning that so not complex. So like this function here, if you have a parabola like this, this function, I guess again I'm changing the color. If you look at this parabola, that has 2 roots, but they're both imaginary. So it's where x equals 0. So there's this one, a parabola by definition has 2 roots and they're imaginary. This function here has 5 real roots. So that's one thing. And also for you approaching this, if you have a function that looks like that, now part of your job as a scientist is to figure out which one makes sense. And but we've already talked about that with quadratic equations. Then, so a couple other things when you look at functions. So this area right here, these are known as local maximums, and these here are local minima. And for both of these, the derivative of the function equals 0. So have you guys had calculus before? So I don't know. Kiana, are you in calculus, or do you know what calculus? Have you ever run this before?
No, not yet.
Okay. So one of the things you'll do when you learn calculus is you can calculate where these local minimum, local maximum are. And they're important because let's say that this is your range and you want to make the most profits. Or this is your range and you want to make the least amount of something that's cost money to get rid of, right? So those are one of the things, the major tricks you can do is do the first derivative. Then you might also notice, just looking at this plot, and I know I'm changing colors on you quite a bit, that this graph right here, we call it concave down. So the graph is concaving downwards. This right here, this one is concaving up, and it concaves down here and it concaves up there. So, and where it changes from concave down to concave up, that's going to be, actually, I wrote kind of these points there. So those points there are where the graphs change from concave up to concave down. And that's also where the second derivative equals 0. Now, I'm sorry, I know some of you haven't had calculus, but just if you can kind of see this, like approaching a function and what the function means, this one is down, this one's up, this one's down, this one's up. Meaning that if you look at this function right here, it's kind of pointing down. And this one here, it's kind of pointing up. That's what I mean by concavity. And that's also where later you can learn in calculus, that's where the second derivative of the function equals 0. So this is important, and I'm saying that because when we do a titration, like a pH curve, you can look at this and there's a point, this point right here, actually the equivalency point is also, oh, and that's called an inflection point. I should say this when you have the concavity switch, that's known as an inflection point of a function. You have an inflection point right here. And I'll show that later and what that, and then there's some meaning with that. So you can, much of this, and the book doesn't really go over this, but it's just kind of like using math kind of like in an intuitive way to solving some of your problems. You can do that trick to just by looking at graphs, you can tell quite a bit of information from your system. So this right here, this is known as a logistics plot, and it's a logistics plot. Not like when you hear the word logistics, you probably think of like, oh, I need to lay my floor tile down before I replace my toilet in my bathroom, and kind of thing, or I have to make sure I have the water run to my house before I connect the faucet. That's what you might think of logistics kind of thing. But logistics in math, it just means a log plot. So this is a log plot. So definition, which is also weird, right? We have words in science and we have words in vernacular, common vernacular, and sometimes they mean the same things and oftentimes they don't. So this is one of those things where logistics means something different in math concept versus colloquial common speech. But so this is a curve it's a logistics plot for a strong base and a strong acid. So if you look at this, so here I am approaching this, and can anyone even you can see that we're adding base. But what's happening here is a titration, meaning you have a beaker of some acid and you're throwing base into it. Usually you use a burette. Have you guys done that at all in lab? Did you use burette? Okay, you have. So you're doing a titration. Did you do it with vinegar? Oh, okay. I always use vinegar. Anyways, so, but if you look at the y-axis, the y-axis is pH, and the x-axis is the amount of base added. And if you notice, you start off at a very low pH, so an acid. So in this case, right here at zero sodium hydroxide added, it's just acid. So pH of 1, meaning that it's a concentration of 0.1. And then you add base, and then it kind of creeps going. Suddenly you have this huge jump, and then you kind of creep, and then you go towards and there's an asymptote here. So if you want another math concept, you have an asymptote right there, and the asymptote is going to be the concentration of the base solution that you're adding. So Meaning if you remember functions, you have an asymptote, that means that the function approaches the value of it, but never quite gets there. And there is a physical thing for this, because if you have a solution like right here and you're dropping down your base into it, you will never quite get to the concentration of the base because you have a little bit added volume there. You can get close to it, you get infinitely close to it, but you can never actually get there. So of course, there's not a true asymptote in this though, because there's a finite amount of matter in the universe. And if you add enough matter to something, it's going to turn into a black hole. So I mean, there's like, there's a limit to this, where the math concepts break down and you have to do with the real world. This is the real world kind of thing, even though I know academia is very hypothetical in general. Okay, so, but I'm trying to connect math concepts to chemistry. And so there's an important point right here. And it's an inflection point, meaning this part of the function is concave up and this part of the function is concave down. So actually this function right here, there are no real roots for this function, meaning the y-axis, I'm sorry, the x-axis is never crossed. So this would be a purely complex function if you tried to describe it using classical algebra. So, but there is an inflection point, like I said, right here. And this is the equivalency point. And the equivalency point is where the moles of acid equals the moles of base. And for a strong acid and strong base, it's exactly at 7. So when you do this, so one of the things you can do, so if you're doing this problem and you're trying to figure out where the equivalency point is, you can do it where the pH is 7, or you can also do it where the inflection point is. So you can kind of look at the graph and figure it out that way. So this is strong acid titrated with a strong base. Here is the opposite, where you have a strong base titrated with a strong acid. So it's very similar. It's very similar, but it starts off concave down and it becomes concave up. So you have the inflection point. Inflection point still at 7, and the equivalency point, that's where the moles acid, or in this case moles of base, equals the moles of acid. So then the number of base particles equals the number of acid particles, and at the equivalency point at 7, it means that they've all destroyed each other and there's no more acid or base on either side. And same rule. Right, so you start off here with a pH of 13, so it's a 0.1 molar solution of strong base. And you're titrating with a 0.1 molar solution of strong acid because the asymptote for the x-axis is at a pH of 1. So, questions so far? So let's talk about a weak acid and a strong base. So weak acid, strong base, the same idea. pH is the y-axis. Amount of base added is x-axis. And interestingly enough, for a weak acid, you have the initial sort of rise. There is a part of the function that you have an initial sharp rise, and you don't really see that. If you look back to the strong acid, you don't have, this is more of a flat. This is a very flat rise. But for a weak acid, it's a pretty hefty rise compared to the strong acid. So you have initially a rise, and then you kind of have this flat area in the middle, and then you jump up, and then you have a flat area at the end. So, but notice something. There is an inflection point here, right? So this is concave down. This function is pointing down, and then it becomes concave up here. And you have another inflection point there, and now it's concave down. So do you see that where you have two inflection points. So where it goes from, are you guys seeing how I'm drawing it, where it kind of, the initial part of the function points down, the middle part points up, and the latter part points down? Are you getting what I'm saying by concavity? Okay, good. So you can see that. So this inflection point here, this is the equivalency point. And so it's a weak acid, strong base. And remember when I said last chapter, when you have a weak acid and a strong base, the salt is actually a base because the base is so strong. When it punches the acid, it's like, I'm a strong base, you're a weak acid. I've punched you and now you're basic, kind of, because I'm a strong base. So you can see that the pH of the strong, the pH of 7 is here. So there's a pH of 7. So the equivalency point is slightly higher than 7. So but then this other inflection point, if you're wondering, this inflection point turns out to be the pKa. So if you do a titration curve of a weak acid, you can actually figure out what its pKa is. So if you want, because you can, yeah, and you can do it one of two ways. You can look at it, and I mean, just for me, I see it around there that goes from concave down to concave up. Maybe it's even a little further over. Let's see if I can figure. Yeah, it's probably, I don't know, around here-ish. I think it's a little past that red line. So I mean, this value is the pKa. So you can kind of, so you could kind of, so this acid, whatever it is, its pKa is going to be about 3.75-ish. So I don't know, I'm just kind of get maybe 3.8, and it'll be pH of about 3.8. So that means it's going to be something like formic acid or hydrofluoric acid. So you can tell a lot of stuff from these graphs. Or the other thing you can do is you can do the those of you that have calculus, you can take the second derivative equals 0. And you have two points where that happens, and the first point is going to be the pKa. The second value is going to be the equivalency point. And then the equivalency point will tell you then, the equivalency point is important because then you can figure out what the concentration is. So this tells you a lot of information. If you look at it close enough, looking at this graph, you can infer. So what can I tell you? If someone gave me this graph, what would I be able to tell that person? I'd be like, okay, this is a weak acid. Its pKa is around 3.7, 3.8. And the number, so the equivalency point, if I know the concentration of the base, I can tell you how many moles of acid there are. So you could infer that just from this, just looking at this graph. So there is a bit of information there. So, but besides the point, why am I telling you about this? There is this area here. Maybe I'll highlight it. There's this area here. You can't see that as well. Okay. Change colors. Can you see pink? Yeah, you can see pink. This area here, I mean, compare it to this one, right? I mean, this pH doesn't change that much. So it goes from like, I mean, maybe 3-ish, more than 3, 3.5 to maybe a little bit over 4, right? So, but meanwhile, you've added close to 20-ish milliliters of base, 15 or 20 milliliters of base, and the pH hasn't really changed at all. So, I mean, it goes up very incrementally. This area here, this is the buffer zone. So buffers don't work over any pH. It works over a specific set of pHs. And also, it's not as pronounced in the middle. right? So if you look at a tangent line here, so tangent line, that's here looking at around the pKa. So the rate is going to be that way. If you look at the pH change here, right, that's a lot more significant. So depending on where you're at in the curve, the pH change is going to be faster on the edges than it is than in the middle. So that's the buffer zone. That's the buffer zone. That's where the pH doesn't change that much. So that's important for a design purpose. So meaning you want to design your solution such that it's in that area. And so here is the other way around. Here is a weak base and a strong acid. So normally though, pretty much all the problems in this class are going to be weak acid, strong base, but just for the point of completion, I'm doing it all for you. So just like the weak acid, you had this initial sort of drop, right? You see this, you have this initial drop, and then this is concave up, and it kind of goes to concave down. So you have an inflection point here, and then concave up here. You have an inflection point there. So same idea. This is going to be the PK. PKB. No, I guess it'll be 14 minus the PKB, because it's going to be a little different because we have it geared towards acids, but you could then tell the 14 minus that number is going to be the PKB of the base. And this equivalency point, so for this one, it's ammonia with hydrochloric acid. So this one's ammonia with hydrochloric acid, and the equivalency point is less than 7, so 7 is right there. So just like the same old things fighting, and I'm sorry if I'm using this, it's just the way I remember it. So I guess I'm teaching it the way I remember it. Strong acid, weak base. I'm going to push you down to a low pH because I'm a strong acid. And so then you have the equivalency point lower than 7, and you have an acidic salt solution. So for there. So yeah, hopefully this helps you when you look at these graphs, that hopefully that makes them more meaningful. Now, what about polyprotic? So polyprotic. Oh, and just like this, there's going to be a buffer range. There's a buffer range here. Maybe not that far. It would be like right around here. So you can have a buffer. It's going to be around 9 from that graph using this. So using it'd be hydrochloric acid, ammonium. It'll be ammonium chloride and ammonia. So you could have a buffer using ammonium chloride and ammonia for this one there. And then the titration of a polyprotic acid. So it's got 2 hydrogens. This is sulfurous acid, H2SO3. So a couple things with this graph, right? So this is concave down here. It's concave up here. Concave down. Actually, no, it's too far. Concave down there. It kind of goes concave up here, then concave down again. So that tells you that there's going to be a Ka here. There's an equivalency point there. There's going to be a Ka2 there, an equivalency point there. So you have here for this function, you actually have 4 places where the second derivative hits 0. So, which means the function is actually, it's going to be x to the 6th or greater. So it could be, the function could be greater than 6 because it could have imaginary roots. But there's at least 6 x's. There's at least this is a polynomial with a value of at least 6. So because I can tell this, because every time you take the derivative, you're going to lose a root. So that means the first derivative is going to have 5 roots. The second derivative is going to have 4 roots. So since we have 4 inflection points, we have to have at least a 6-degree polynomial. But okay, but now besides that, there's buffer zones here and there. So meaning you could use sulfurous acid depending on what buffer range you wanted. If you want a buffer of about 1.7, 1.8, you could then use H2SO3 with HSO4 minus. If you want a buffer that's in the high 7s, you could use HSO3 minus SO3 minus 2. So you could use solutions of those two to design a buffer. So it just depends on what you want. And I'm kind of, for this year, I'm not going to ask you to design a buffer looking at the system, but I'm just saying future, if you have to do so, let's say you have to grow bacteria. One of my sisters, she got a master's in environmental engineering, and she had to grow some bacteria. And it was a tough thing because she and her lab partner, they had to negotiate like who was going to go, especially for Christmas, because you can't just leave for 2 weeks because then the bacteria dies. So you have to make sure that the bacteria are fed, and you have to make sure the buffer is maintained, because if its pH jumps up or down, bacteria die. So she was using buffers. She was making sure that the bacteria had food. And it's not something that you can just like, well, guess I'm gonna go away for Christmas. See you later, 2 weeks, hope you don't die, bacteria. Yeah, the bacteria will die. And then all the research dies with it, kind of thing. So you have to figure out which pH the bacteria like, and you got to design a buffer to make sure that the bacteria stay at that level. So that's that's an application for this. So hopefully that makes sense. How are we doing? Those are questions with this? So hopefully that's making more sense. Like at least as far as I mean, kind of combining math, and I know you probably did they teach math at all like that to you guys, like in high school, or do you ever look at functions and say I had a teacher was like that. If someone said, hey, here's a function, and this is my function, what can you tell me about this function, kind of thing. So what does this function mean? And well, I can tell you, looking at this function, that there are 1, 2, 3, 4, 5, 6, 7, 8. There's 9 roots. So this is at least x to the 9th power or greater. I know that there is asymptote here. So meaning it's going to be a fraction. So I'm really having something that's x to the 11th over something that's x squared, or higher, because there's going to be the denominator has 2 values where it's 0. So because then you have asymptotes approaching. Oh, actually no, I guess one would go positive and negative infinity. I drew this wrong. I drew the middle part wrong. Oh, I'm sorry, Mr. Harding, my old teacher. He would be rolling over in his grave, right? Unless he's still alive. Maybe he's still alive. If you're still alive. So this one it would then go here. So are there a number of roots? Yeah, right number of roots. Okay, and then if you I'll do red, I'll do. So then you have these areas here. We have local minima and maxima. Then you have where the second derivative, the first derivative hits 0. 1, 2, 3, 4, 5, 6. So you have the f prime equals 0 at those points, and then you have inflection points. So here, I guess there's an inflection point there, so you would have a second derivative there too. So there. So you'd have points there where the second derivative equals 0. So that's like, if you can approach math that way, it can kind of, you know, just looking at a function, you can just look at a function and kind of get some intuitive information about your system from that. So I know that's, there may be some applications. There's certainly applications for that in this class, but hopefully some of that you can think in the future when you look at a function and kind of, you can kind of, you know, mine data from it just by looking at it. And that's one of the powers of having a graph. So, but do they not, I think I was taught a little old school, at least, or literally old school in this day and age, but kind of like, he was a very old fashioned teacher in that regards. But were you guys ever taught to look at functions that way? Yeah, I guess not. Okay. Well, hopefully it helps. Another toolkit for you. So, have we any other questions? So, looking at time, and do I want to start the next part? I guess I could. You know what, though? I think no, I'll go ahead and do it. We got 10 minutes. I can explain this. I was wondering if I should end class early, but I guess I can still finish at least one of these concepts in 10 minutes. I can always just go quickly over next time. So now we're going to move away from acids and bases. So buffers are, you know, they're acids and bases, but an area where the pH doesn't change very much. And a combination of a weak acid conjugate base or weak base conjugate acid. So now we're going to go to talk about other things. So there's other things that are in equilibrium. So it's aqueous equilibrium, not just acids and bases. And if you remember, we talked in Gen Chem 1, we talked about solubility rules. Actually, I can even go back to that. Chem 161, I think it's chapter 5. Here we go. Funny how it popped up. Exactly what I wanted. Do you remember this stuff with the solubility rules? So if you remember the solubility rules, to figure out if something is soluble or not, and for instance, you'd say that calcium carbonate from this, calcium carbonate is insoluble, meaning it does not dissolve in water. But then you go and have you guys ever been to like the mainland or other, not just US mainland, but anywhere where they have caves, where they have stalactites and stalagmites? We've never seen those, right? So you have stalactites and stalagmites. So like you go into a cave and sometimes you see columns, sometimes you see a straw or something, sometimes you see something that looks like this. Like you can get various things with a cave. Actually, the stalactites which one's on the top? I think stalactite is on the top, right? I'm not sure actually. But it starts out when it grows, it starts out as a straw. And the idea though is you have water trickling down, and the water has, as it's trickling down, actually a little bit, calcium carbonate is limestone. A little bit of limestone dissolves into water, ever so a little bit. But as water is dripping in a cave, here's your water droplet. If and some of it evaporates, and then what happens is that it gets a little bit in there, and then you can get precipitates of calcium carbonate into it, because calcium carbonate being in water, it's actually, if I can do this properly. Is actually in equilibrium so you can have a little bit of, it's an equilibrium where you can get a little bit to dissolve. It's very, very small, very, very small, but it dissolves a little bit. And you can then, when you have in a cave, you can have water, groundwater coming, from the surface going on down, and then the groundwater dissolves a little bit of calcium carbonate, especially if it's acidic rain. And then as it's dripping into caves, the water droplets will then evaporate a little bit and can precipitate down calcium carbonate. And then this is the growth of it. It forms straws first, and then it forms kind of, I think the tite is on the top, but then the water is still dripping down. So then you can start to form a pile of stuff, and it grows and grows. And eventually it kind of looks kind of like a double-sided tree trunk over time. So, and what governs this is the equilibrium. So coming back to chemistry this semester, we can have equilibrium with this. And for instance, fluorite. So calcium fluoride. It's insoluble. We'd consider it insoluble, but it's ever so slightly soluble. It's an equilibrium. A little bit of it does disassociate. And then with this equilibrium, so breaking apart, we have the products over reactants. So the calcium ion plus the fluoride anion concentration squared, because there's a 2 there. So, and then over the concentration of the solid. But then with equilibria, we don't include solids and liquids in the equilibria. Therefore, the solubility product constant, or the KSP, is just then the ions, calcium plus 2 concentration plus or times fluoride squared, because of the 2 there. So preview then for Wednesday, we do molar solubility. I guess I can crank this one out. What the heck? So the solubility product constant for lead chloride is 1.7 times 10 to the minus 5. What does the molar solubility mean? How much lead chloride can I dissolve into water? So initially, we write the equation: lead chloride equilibrium, form lead ion and lead plus 2 ions and 2 chloride anions. Change, this is going to have 1 molar solubility. So problem with me, my S's look like 5s, so I usually use the $ plus 2 S's for that. So 2 solubilities, 2 extent of reactions for chloride. Equilibrium, we're going to ask 2 as KSP is 1.17 times 10 to the minus 5 equals solubility 2 solubility squared equals 4 solubility cubed. So common mistake, don't forget to square the inside. So that means then that 1.7 times 10 to the minus 5 over 4 equals the molar solubility cubed, or the cube root of that equals the molar solubility. So then we'll talk about this more. I just wanted to show you the setup for this. We'll talk again more about this on Wednesday. So I guess rather than putting class out early, I decided to give you previews for Wednesday. So come again and learn more chemistry. Coming soon to a chemistry classroom near you. Molar solubility and aqueous equilibria. So, all right, then, if there's nothing else, I think I will end class now. Any questions? Nope. Okay. I will end the recording then.